In this video, we'll be looking at Chapter 14, Section F on inverse functions. Remember from the previous video that we were looking at transformations of functions. And we had three different types: translations, dilations, and reflections. We're going to take a look at one of those reflections in more detail in this video. Namely, the reflection of y equals f of x in the line y equals x. So really quickly, remember we had a graph of the function y equals x squared, and if we took the mirror or the reflection of that graph, it looks like this about the line y equals x. Well, this is a special function or a special transformation, and we're going to give it another name called the inverse function. And the notation for the inverse function is still the same f, but in this case we're going to use an exponent of -1, much like inverse cosine, inverse sine, and then close parentheses with an x. Right, so this is the inverse function of f of x. And again, the inverse is the initial function reflected across the line y equals x. Now the inverse function has a few special properties. If we take a composite function of f and the inverse of f of x, like so, this simplifies down to just x. And this is true for any function that has an inverse function. Likewise, if we take the inverse of f of x, this also equals x. And again, this is always true for any function that has an inverse. Now, practically speaking, to find the inverse of f, we simply replace x with y and y with x. So essentially we're swapping y and x. And we saw this when we were looking at the reflections in the last video. So let's take a look at an example. Here we're given a function f of x, which equals 1/2 x minus 1. And we're asked to find its inverse, and then to find the composite function f of the inverse of x. Let's start with finding the inverse. So again, we're simply going to replace y with x, and really I can write a y right on top of f of x. So I have this equation y equals 1/2 x minus 1. And I really just switch x and y. Okay, and now I need to get y by itself again. I need to solve for y. So I'm going to move 1 over to the right hand side. So I have x plus 1 equals 1/2 y, and to get y by itself, I'm going to multiply both sides of the equation by 2. And so we have y equals 2x plus 2. Now that we know the inverse of the f of x, and one thing I forgot to do was to replace that y with the inverse of x. Okay, now that we know the inverse, we can find the composite function down here. Remember, I'm going to take this function and place it into this function everywhere I see an x. And so my composite function equals 1/2 times 2x plus 2 minus 1. Well, distribute that 1/2, and we get 1/2 times 2x equals x. 1/2 times 2 is equal to plus 1, and don't forget the minus 1. And look what happens, that the 1 and the minus 1 cancel, and I'm left with just x. And we had said that that would happen, but here's the proof. Here's an example of how that works. And again, that is always true for these types of composite functions. The inverse of f of x and f of the inverse of f of x, although that's kind of a tongue twister, those both will equal x all the time. Now really quickly, let's graph those two functions, f of x and the inverse of x, to see what they look like. So our first function, f of x equals 1/2 x minus 1, is a line, and it crosses the y-axis at -1, so I can put a dot there, and I know that its slope is 1 over 2, so it means it goes up 1 over 2, up 1 over 2. It can also go down 1 over 2 in the opposite direction. And so this is my first line. This is f of x. Okay, and the inverse of f of x is 2x plus 2. So this will cross the x-axis, the y-axis at positive 2, and my slope is 2 over 1, so I'm going to go up 2 over 1. I can also go down 2 over 1 in the opposite direction. Okay, and so this is my inverse function. And remember, these are supposed to be mirrors across the line y equals x. And y equals x crosses the y-axis at 0 and has a slope of 1, so I go up 1 over 1, up 1 over 1, up 1 over 1. I can go the same in the opposite direction. And if I draw that line, y equals x, notice that the two lines, f of x and the inverse of f of x, cross at a point that is also on that line, y equals x. And that makes sense because I'm mirroring these two functions across that line, y equals x. And so one of the points that is common, or the only point that is common to those two graphs, is -2, -2. And you can plug those coordinates into each of those functions and you'll get the same values.